we can start. So the first thing I want to mention is the first homework is due today at midnight, and now you have the second project up as well. So again, if you have questions about the homework, you can email me, we can Skype. But today we will see how much we can do. Or come to my office. So do you have any questions to start off with? No? Okay, so let me quickly pull up the project. And this project is 20 points. So 20 out of 100 of your full grade. Okay. It looks long, but again, there's nothing in here that you haven't already seen. And everything we have talked about up until now, you will use here. Everything we've talked about in terms of stability, discretization, solution methods, you will use all of it in this project. And it's only 1D problems, not 2D yet. Okay. So the first problem is basically you're given the heat equation and you're given initial and boundary conditions, and you're given everything and you have to write code to solve it. Okay. And you have instructions on what to plot and what to show. Okay. Then there's also, remember we were talking about order of accuracy. So here you will compare to analytical answers, and that will help you compute what your order of accuracy is for different schemes. Well, for the particular scheme that you will use. And then there's also an analytical solution that decays in time. So here you can compare how your numerical solution changes in time versus what an analytical solution would look like. Okay, and finally there's a problem with an inhomogeneous boundary condition. So there what's happening is you have a rod and one end is held at 0 and the other end you keep changing the temperature as a sinusoid. So you make the temperature go up and down. And then you will see how the heat propagates through the rod. Okay, so those are the three main problems. And you have roughly 2.5 weeks to finish. Okay, so again, there's nothing new here. Everything should be very familiar to you. The instructions are again here. Any code you write should be uploaded to Git, and the PDF, movies, everything. You can zip up and put it on Canvas. Okay, so again, I guess you will need to read through this, and I can ask you if you have any questions next time. Okay.
Professor, what's the exact due date?
The due date for this is
February 7th.
Yeah, February 7th at 11:59 p.m. Okay, so today we've been talking about the heat equation for a long time, right? And you might be wondering why. What does it have to do with fluid mechanics? And if you remember, our conservation laws are conservation of mass. Can you see that? So anytime we solve the physical equations, we are looking at conservation of mass. Do you remember what this was for incompressible flow? Yeah. Go ahead. So it simplifies to a very short term, right? Do you remember? We derived the whole thing from the basic equation and came up with a very short equation. You might have also heard of it being referred to as continuity.
Del rho by del is 0.
For incompressible flow. So for incompressible flow, in terms of velocity, right? There was a condition on velocity. For incompressible flow, conservation of mass simplifies to this.
Dot u.
Yeah, exactly. Lambda dot u is equal to 0, right? And we derive this, and this is what will keep appearing over and over. So that's the first law. The second law is conservation of momentum. Right? And now we're talking about the Navier-Stokes equations. They govern fluid flow. Navier-Stokes. Okay. So conservation of momentum looks like this. We have time derivative. Okay, so there's this long equation, but we know physically what each individual component means. Do you remember how we can simplify this left-hand side? Do you remember the material derivative? So the material derivative was basically del of anything phi is equal to del phi by del t plus u dot lambda phi, right? So this is the definition of material derivative. And if you recall, it just represents how a blob of fluid that contains this thing called phi can be a chemical species, it can be temperature, how this phi on the blob of fluid changes in time. So you will notice that this left-hand side is very similar to what's written here, right? So we can rewrite the Navier-Stokes equation as V over rho plus lambda squared. Okay. Now things should look familiar to you. Do you remember this equation is what we keep talking about over and over and over again?
Diffusion?
Yeah, this is the diffusion equation we've been talking about, right? Mu del 2t over del x squared. The lambda squared is just general in 3D in any dimensions. You can write it as that. Okay. So this is the diffusion term or velocity. Also called, do you know what it's called? Do you know what mu is called?
Kinematic viscosity, what is it?
Yeah, this is the kinematic viscosity. So this term is the diffusion term or the viscous term. Okay? And the left-hand side is basically telling you how u is advected in the flow. So this part is called the advection term. Okay. And when we solve this Navier-Stokes equation, what we do is we do it one by one. So your steps would basically look something similar to this. So first, you solve for advection. Of u, and then you solve for diffusion, and then the only term remaining is the pressure term. Then you take care of the pressure term. Solve the pressure term. And we will see how we do this one by one. Okay? Now, there's one problem here, right? There's a very big problem that has been the bane of fluid mechanics for decades. You can see that right here. Okay? So if you look at the advection term, there's something different between this left-hand side and this term over here, right? Are you familiar with linear PDEs and nonlinear PDEs? So, what is this one? Is this linear or nonlinear?
The first term is linear, right? The second term
This
is not.
This whole right-hand side is not linear. I will tell you that phi does not depend on u. Okay? Phi is not a function of u. Phi is a function of x and t, but does not depend on u directly. Okay?
So it's a summation of, the first one is linear, we can say phi over that's linear. Second one is non-linear, so the whole right-hand side is non-linear. Is that?
Okay, wait.
The first term, is that the first term? Partial phi over partial t.
Okay, so you're saying this term is linear and this term is not linear.
Yes.
That is correct only if phi is related to you. Here, phi may not be related to you, right? Phi may be independent of you. So if phi does not depend on you, it's called a linear PDE. Okay? And you will already notice here that this u is u itself. So it's a nonlinear PDE. So solving the nonlinear PDEs is a big challenge. And that's why there's no analytical solution to this yet. Okay? You can analytically solve this, the advection of phi, if phi does not depend on you. Okay. Now, again, does it seem strange to you that phi is like a chemical species or a blob of ink I drop in the water and it does not depend on you? Does not make sense. Does it make sense?
No.
Does not make sense. Does it make sense to somebody? So it actually does, because when you drop that blob of ink into a glass of water, the only reason the blob gets moved around, if we ignore diffusion, is because there's a velocity of the water itself. So if you start stirring it, and blob of ink is a bad example. If we drop like a small plastic bead in the water, and the only reason it will move is because of you, right? But the bead itself will not get deformed the mass of the bead does not depend on you. It's just getting affected. Okay? So that's a linear case. But when the thing inside depends inherently on you, then that's a nonlinear case. Okay? I hope I didn't confuse you too much. Okay, so the point is, if you have linear PDEs, they are much easier to solve compared to nonlinear PDEs. Okay, so I will show you a few examples of this advection. Okay, and these are simulations I was doing when I was basically starting out in computations. So what we have here is blank screen. Yeah, all right. So what we might have here is you might have this scalar concentration. This is a two-dimensional field. So we might be looking from the top, and this is just a tank of water. And then we put a blob of ink in the center, right? And this represents the concentration. So it's most concentrated at the center, and slowly you get pure fluid. Make sense? And if we start advecting this with a constant velocity along the diagonal, this is what will happen, right? Again, in this simulation, there's no diffusion. It's pure advection. So it makes sense that the blob should not change. It should not diffuse in time. It should not get deformed. Shape should stay the same. And this seems like an easy thing, right? It's an easy thing to achieve. So any sort of scheme you implement should be able to do this. But it's, again, this very basic test is not very straightforward to do. Let's see. So if we look at after 10 rotations, what happens to the flow field, or not the flow field, to the blob, it starts getting deformed. And when you see black patches, it indicates negative concentration, which is unphysical, right? You should never have negative concentration for a species. That's like antimatter. So why does this happen? These are just 4 different numerical schemes. So there might, in terms that we might use different type of discretization. For one, we might use a second order accurate discretization, third order, etc. So why does this happen?
And there's no diffusion term?
There's no diffusion term. Even with diffusion, you would still see these sort of errors. Your shape would get deformed, right? See here, this thing is not a perfect circle. It looks splattered, and here there's some sort of an egg-shaped. Look closely enough. This one seems to work well. Okay, so even if you put diffusion in, physical diffusion, these errors don't go away. They might be more difficult to see because diffusion smears out everything. So it will smear out these errors. So these are exactly the numerical errors we've talked about. These are you remember when we approximate derivatives, there's some terms that are missing. There's an order delta x squared term or an order delta x cubed term. And those missing terms are exactly what causes these sort of errors. So these are numerical errors. And let me see. This is right. So this is again another scheme. Wait. Let me show you somewhere where it's a lot more evident. Okay. Okay, so I will, if you want to see what happens very clearly, what you do is you take a very coarse grid, and then you run your simulation on there. And with that, the errors will be very, very evident. Okay, here you see our blob almost immediately disappears completely. So that's looks like physical diffusion, but it's numerical. It should not exist. Okay, and again, we will see later on how exactly our truncation error relates to this diffusion. Okay, so that's one scheme called, the name is, or can you see? Yeah. The name is book 1, so it's a first order scheme. If we go to a third order scheme, what happens is, yeah, fine, now the diffusion goes slower, but eventually if I run it for long enough, the blob will diffuse out. If I use another scheme called semi-Lagrangian order 1, again, you see, almost immediately it disappears. But if I use a third order, now you'll notice that the blob stays. Okay. So this is where the scheme that you pick to discretize becomes very important. Another example that we can look at is this one over here. Again, it's a very simple test, right? And does this make sense? Do you know what's happening here? Let me go to the beginning of the movie. Okay. Okay. So the colors just represent the concentration, right? So you can have 100%, let's say, fuel, or yeah, which is not burning yet, and this is pure air. Okay. And it looks like there's a vortex field at the center that's trying to mix these two things. Okay? And this is a very simplified sort of case that you can use to study mixing of air and fuel. Okay? A very, very simplified case. So this would be what you would turn to test your code very quickly. Okay, so again, does this make sense? What should happen as the vortex starts turning the fluid or the scalar? This is called a passive scalar. Passive scalar, that's important. Okay, I will write it when I switch. So a passive scalar is basically something that does not influence the flow field, but gets affected by it. Okay. So tell me, intuitively, what should happen? In reality, what happens when this sort of mixing takes place?
It should all turn green,
It should all turn green, right? Because of
the mixing.
mixing. And mixing is basically caused by diffusion.
Mm-hmm.
Right? Physically, when you put a thin strand of air and let's say fuel next to each other, there's a very sharp gradient. So things will want to diffuse out very quickly. And if you leave this thing running for long enough, eventually everything will be green. The whole concentration field will be uniform. But without diffusion, if you don't implement any diffusion, what should happen? Numerically, if you don't implement physical diffusion, what should happen?
You're going to have a thin gradient between the layers.
Yeah, the scalar will keep getting stretched into thinner and thinner filaments, and it should not diffuse out. Okay? The only diffusion you will see, if any, will be because your numerical scheme has some errors. So let's play this and see if we see any diffusion. Okay, so we're getting very, very thin filaments, and if it gets too thin, then yeah, it goes to yellow and then eventually green. Okay, so this is unavoidable. It will happen. Our job is always to minimize this error. Okay. If we look at some other schemes that I was playing with, you can see that this sort of numerical error happens very quickly. So let me see. Yeah, this one should be a good example. So this is a first order scheme, and let's play from the beginning. Okay. All right. You see, as soon as the filaments start getting thin, it diffuses out because again the gradients are large and the truncation error terms become huge. Make sense? All right. Let me play another one. This is also a first order scheme. And again, you see, okay, it disappears. You can clearly say that this result is not correct physically. Okay? And this is the nice scheme that I was implementing. This is a third order semi-Lagrangian scheme. And this stays for quite a while. Okay, so again, these are very simple tests, but they are very essential to make sure your code works the way it should. Okay, any questions? Okay. Let me see then. Okay, so we've talked about diffusion a lot, diffusion equation a lot, which is the lead equation. Today we will take a look at the advection equation and how to discretize it. Before I go there, I just want to point out, last time I was a little getting ahead of myself. And so if you remember, we scratched this out. Turns out that we were on the right path. Okay? We just needed 2 more steps to get to the answer. So let me very quickly just rewrite this. Yes. Okay, so this is the stability condition for, so this is recall. And the videos I was showing you, you will implement something similar to that, or again, for one of your projects, the advection of the scalar. So stability condition for the heat equation, explicit heat equation was all right, so up until this point we were fine, which is 1 plus alpha delta t over x squared times 2 cosine k delta x minus 1 should be less than 1. Okay, and we use 1 minus cos k delta x equal 2 sine squared k delta x over 2. Okay, we substitute that in, we get 1 plus 4 alpha delta sine squared k delta x over 2 is less than 1. And we know when we get rid of the modulus, we have to do this.
I think that's minus.
There's minus? Yes, yes. This is 1 minus cos. Yeah, this is a cos minus 1. The 1 minus cos will give us a minus. So there's a minus. Yes. Thank you. Thank you. 4 alpha delta x squared sine squared k delta x over 2 is less than 1. I'm just doing mindless algebra, so there's nothing fancy happening here. K delta x over 2 is less than 0 and greater than minus 2. Okay? So we know this cannot be negative, this must be positive, this must be positive. There's a minus here, so this is always true. Okay, now, so the remaining condition is over here, and if we take minus 4 to the other side, it becomes f is greater than alpha delta t over delta x squared. And this is the condition, right? This is the stability condition. So yeah, we just had to go 2 more steps and you would have been at the answer. Okay. All right, all this is tedious mathematics, but once you know where it comes from, it's very easy for you to go back and do this for other schemes. Okay. All right, so let's go look at the advection equation. Okay. Pure advection. And let's stick with the linear case. And the animations I showed you were for the linear case. And are there any questions? No. Okay. So pure advection actually looks like this: del phi by del t plus lambda dot phi u equals 0. But again, since we are dealing with the incompressible case, we will always make use of lambda dot u equals 0. Okay, so if I break this up, it just becomes this phi lambda dot q plus u dot lambda phi equals 0. And this we have said is 0. Okay, so then that's what we get, the d phi over dt equals 0. Okay. All right, so we were talking about this material derivative just a moment ago, but can one of you remind us what this term means? D phi by dt equals 0?
Incompressibility.
Incompressibility is the one we used here, right? Lambda.u equals 0, right? Physically, do you remember what the material derivative indicates? In terms of like blob of fluids?
The mass doesn't change.
Yeah, so if you say this is, if my phi here, the general variable, if I call this to be rho, the density,
Continuity.
then this would be continuity, right? This would be d rho by dt equals 0, which again goes back to it's incompressible. But now my phi can be whatever. Phi may be one, concentration of a chemical. Okay, it can be concentration of ink blob, right? The ink that's being dispersed. It can even be temperature. Okay, so any passive scalar, phi is any passive scalar. And passive scalar means phi gets advected by fluid U, but does not impact U. Okay, so phi will follow what U says, but the change in phi has no impact on U. Okay, that's what happens in a and if you drop a blob of ink in like a rotating glass of water, okay, the blob of ink will start rotating and diffuse out, but it will not influence the velocity of the rotation. So that's what the passive scalar means. Okay. Now, again, it should seem strange to you that temperature here is a passive scalar. Does that make sense?
Yes.
What happens if you heat a fluid?
The density changes.
The density changes, it might start moving because of buoyant convection, right? But that sort of effect needs that you have buoyancy, right? So you need acceleration of gravity to be included in your momentum equation. And usually we don't do that because the acceleration of gravity is very small compared to all the other terms. Okay? So if the temperature change is not huge, you can assume that this temperature is a passive scale. Or let's say 40 degrees centigrade or 50 degrees centigrade. Okay? So that's the pure advection equation. Okay? Now, how should we discretize it? Tell me your favorite discretization and we will do it that way. So let's see. So this is, let's discretize the okay, so we have del phi by del t plus u del phi by del x equals 0. I have assumed one dimensional. Okay, so tell me, what do you want me to write next? How should we discretize the time derivative? All right.
Was it forward or central?
All right, let's use forward as you said. So we will say phi what?
Phi I n plus 1 minus phi I n over t. What is it?
Delta t,
Delta t.
right? And the second one, this space term, how do you want me to discretize it?
Well, we have to go forward, right, if we did the other one?
You have to go forward, so you were saying
The
something
same
like,
method.
what's more?
Then we have to do the same method as,
As this?
yeah.
No. Remember when we were talking about time, so if we were talking about temperature, this was what we were using, right? Alpha del 2d over del x squared. In time, we were going forward, n plus 1 minus dn over delta t, right? But in space, we were going second order, right? That's what we did. Ti plus 1 minus 2 ti plus dn.
But I think the order of the whole equation is first order. That's the maximum error. You know, first order has higher error compared to central, to the.
Right, yes, okay. So all of these are things we have to be careful of, everything you're saying. So remember, here we used a first order, right?
Oh,
But the space was second order.
okay, yeah,
And so you're not restricted to using one versus the other.
okay.
And what you're saying is this equation is first order? What were you saying?
The combination of these two, you know, the error, truncation error, is the first order.
For
because-
time, yes. Or if we write time like this.
What about the combination of those? Can we say, because we are adding two terms, one of them is first order, the other one is second order,
No. I see what you mean. So your question is here, one term is first order and the other one is second order. So the total computation should be first order, right?
Yes.
That's your question.
yes.
But see, here it's first order in time. And this is second order in space. If you remember, order of accuracy means how fast the error will decrease. So this is saying if I decrease my delta t by half, the error will be half. I have done nothing to space it. If I say I keep my delta t the same, but I decrease my grid spacing to half of what it was, the error will be
1/4.
1/4, right? It will be 1/4. So these are independent. There's a there's a grid convergence in time, and there's a convergence in time, and there's a convergence in space. And on the project, you will see this exact thing. You have to figure out using graphs that your implementation is first order in time, but second order in space. Okay? So these are independent things. Okay, so if we come back here, so this is first order. Let me write this in a different color. First order. And for time, for space, see this is in time. For space, let's start with the second order discretization. Okay. So what is the second order discretization of the derivative?
Implicit or explicit?
Let's keep it simple. Let's do everything fully explicit.
So for n plus 1.
We'd have the u in front, right?
Okay, there's a u, and u at what?
N plus 1, or
Let's
Is this a
do a
constant?
completely explicit thing first, okay? So the time, let's pick n for everything. Tell me the grid, okay? What
I.
grid point?
I.
Exactly. So I'm looking at one particular grid point. This is ui. What will the space derivative become?
Phi I plus 1
Okay,
at
phi.
time n
All right.
minus 2 phi I n.
That is for the second derivative.
Oh,
So just by IN.
All right, phi I, and if we take the second order, it will be I minus 1, right? It's one left, one right, and then that's the difference. Over 2 delta x. And after we are done with this, we will do exactly what you said. We will take phi I plus 1 minus phi I, right? And we will see what happens. So this is second order in space. So it's a very nice scheme. It should give us a very nice result, right? Wrong. This scheme is unstable, and just by looking at this equation, we cannot say anything about the stability, right? So if you actually go ahead and implement this in your code, you will see that the solution after a few time steps will blow up. You will get all infinities and auto numbers. All right, let's see how that happens. Again, we have to do the tedious but elegant von Neumann analysis. All right. So let's do the von Neumann analysis of this discretization. So we remember that whenever the PDE is linear, the error basically follows the PDE of the original PDE. So error epsilon I, let me call it J, Jn satisfy the same discretized PDE. Discretized equation. So we have epsilon j n minus n plus 1 minus epsilon j n over delta t. Then we take that to the other side, minus u j n epsilon j plus 1 and minus j minus 1 over 2 delta x. Okay, I haven't done anything fancy yet. Now, if you remember, we said, let's express epsilon as what? There was a time-dependent term and a space-dependent term.
The analytical solution minus the.
Oh, g of t and e to the I k.
Yeah, exactly. So we will say this is, let's say, g of t and the Fourier mode, right? The Fourier mode. So this is a Fourier mode. And then when we plug this into our equation, we will see how it grows or decays in time, this error. Okay? So let's go and plug this in. So let me just leave this as epsilon j n plus 1, and this becomes g e to the I k x over delta t equal minus u j xj x is fine, yeah, xj or x, okay, u j n over 2 delta x, and inside we get, no, is it g, I wish I hadn't done that, okay. Is it g and e to the I k x here, and inside we get I k delta x minus e minus I k delta x. Is there a mistake? No, not yet. Yeah, it's fine. Okay. All right. So this is basically epsilon j n. This is basically epsilon j n. So what we get is epsilon j at n plus 1 equal and inside we have the first term is cos k delta x plus I sin k delta x minus cos k delta x minus I sin k delta x. Okay. All right. If you see a mistake, stop me. See, there's no mistake, right? Yeah, no, this is fine. So this cancels that. And then we have epsilon j in over epsilon j n with 1 plus u delta t over 2 delta x times 2I sin k delta x. Okay, this is just a plus ib, all right? And we know that we need modulus of this should be less than 1, right? So we need a plus ib, which is basically square root of a squared plus b squared, should be less than 1. Okay? So let's see if that's the case. Square root of 1 squared plus u delta t over delta x whole squared sine squared k delta x should be less than 1. When is this satisfied?
The second term is less than.
No, the whole thing, right? So see, we said the ratio is this 1 plus an imaginary term, right? And I just said a is 1, b is this whole imaginary term. And we know we need the modulus of the ratio to be less than 1. So square root of a squared plus b squared should be less than 1, right? So that's how we got this term. So 1 squared of that term, right? Should be less than 1. So when is this satisfied?
The second, I mean, the term in the, it has to be less,
It has to be
Zero.
0.
Okay?
Yeah, it can't be negative.
Yeah,
It's weird.
that has
That
to
can't
zero.
be.
right? So this can never be possible, right? This is greater than or equal to 0, okay? So this inequality can never be satisfied. Which means the scheme we picked is
Not the same.
unconditionally unstable. It will never be stable. So if, I mean, the first time I saw this, it surprised me a bit. It's a very innocuous looking equation, right? It's this one right here. First order in time, second order in space, everything seems reasonable. And when you do this analysis, you get that this scheme is unstable. So now you see how effective this von Neumann analysis can be. And yeah, if you implement this term, solve it in MATLAB, Fortran, whatever, you will see that this is true. This scheme, no matter what you do, will be unstable if you do a pure vector. So how should we fix this? You know one way to fix this, right? We've talked about one way to fix this.
Implicit.
Yeah, you can switch to an implicit discretization. The disadvantage is it's higher computational cost. But, you know, it's a fix. Another thing is we can try another discretization, fully explicit. Okay? So let's try something else. Okay? Let me see, do I need to tell you anything else before then? No, it's good. Okay, all good. Alright, so now let's make use of our intuition for a little bit. Okay? If I say I'm looking at a one-dimensional flow, right? So there's a straight line and I have velocity everywhere. So there's, let's say velocity here is this and it's slowly decreasing. Here it will go to 0. So this is u at all the grid points. I equal 1, 2, 3, 4, 5, 6. Okay? Now, physically, if you think about it, if I am at node number 4, which direction is information coming from? If I'm over here, what is the direction of flow of information? Okay, if we think mathematically or physically.
3.
What happens here came from
3.
3.
3, right? So my important information comes from the upstream direction. Okay, upstream. Upstream for 4 would be the left side. If we keep going and we say that at some point the flow reverses direction, and now this is what we see. So let's say this is node number 20. So for node number 20, the information is coming from the right hand side. So we would bias towards upstream direction. And there's a technical term for this, it's called upwinding. Okay, you figure out where your upwind direction is and you prefer that. Okay? So here you will bias this way, and here you will bias this way. Okay, I've just drawn a box of arbitrary size. The size will actually depend on your discretizations. So let's redo the discretization with this sort of upwinding. Okay? And so let's redo discretization for I equal 4, but with upwinding. Okay, so let's see. Now, let me write out the equation quickly. So it's del phi by del t plus u del phi by del x equals 0. Alright, this time you will tell me the discretization. Let's use the same first order in time and let's change the space. Okay, so what goes here?
The I n minus
Y minus?
yes. We should
So-
go backwards, right?
When we talk about upwinding, we're only talking about space, okay, not in time. Okay, so here we look at the space direction. So this is in space, right? Which direction the flow is coming from, and we will upwind in space. Okay, so the time we do as we did for the previous case. All right. Tell me.
Minus 1.
Plus 1 for the right this. Okay, and we're still using a fully explicit scheme just with upwinding for the time, space derivative.
UIN
Okay, use the n.
J.
All right, Nicole, you were saying.
The phi j plus 1.
All right, phi j plus 1. All right, now let's go and see. Should it be j plus 1 or j minus 1?
Oh, it's minus 1 because we're going back.
All right, so if we want to find the derivative here, you want to use this and this. right? And I equal 4. So what would you do? And positive x direction is this, right? So to find the derivative in this region, you would do 3 minus 4 or 4 minus 3?
4 minus.
All right, perfect. So that, our
So I minus.
j, yeah, minus.
J.
2 delta x? No, 1 delta. Yeah.
But you.
Makes sense, right?
But in time is you didn't change it.
No, in time, we keep the same. We just, for upwinding, we just look at which direction in space is the most useful one. And here, the left was the most useful direction. We can say for u, j, n greater than 0. That's what we see here. Okay, now give me the other direction. If u, j, n is less than 0, what happens? Time does not change, upwinding only affects the space derivative. Okay, you tell me, what goes here?
UJN.
UJN, yes?
Phi j minus 1.
All right, let's see why. Let's go to our diagram again. So this is the negative u case. Which one would you pick if this is your point of interest?
Plus
All right.
JN.
Yeah, exactly. So you do 21 minus 20, right? So this would be j plus 1 minus 5j. So this is basically how you would discretize in an upwinded manner. Each grid point, you have to check what the velocity direction is, and then the discretization adapts according to that. Simple implementation, implementation is a little more tricky, but it's a very simple concept. And it really helps in terms of stability. And I will promise you this is the last stability analysis we will do. Okay? By now you know enough to be able to repeat this by yourself. Okay, so let's look at stability. Let's take the first case, when u, j, n is greater than q. Okay, so what we have again, epsilon x comma t is some g of t, e to the I k x. So we get phi, epsilon j n plus 1 minus g e I k x over delta t plus, what's the one here? Let's see, it's this one. So I would write as, let me just write it as uj, and there's a g and e I k x. And inside we're left with, there's a delta x over here. Inside we're left with 1 minus k delta x. Make sense? Yeah, I haven't done anything fancy. Okay, so. Okay, again, we will move stuff. So this becomes epsilon j n plus 1 is equal to, actually, let's see, epsilon j n. And this is 1 plus q delta t over delta x. I've just rearranged this. So this means we need and this becomes 1 minus cos minus I sine q delta x. It should be less than 1. This should be less than 1. Okay. Okay, now it gets a little interesting. Let's see. Okay, let's say say u delta t over delta x is alpha, and k delta x is theta. So we have 1 plus alpha into 1 minus cos theta plus phi sin theta less
Isn't
than.
the cosine negative theta?
Yeah, cosine minus theta is cosine theta.
Oh, yeah, yeah.
Okay, all right. So yeah, please, if you see any other mistakes, please tell me. So this becomes 1 plus alpha minus alpha cosine theta plus I alpha sin theta. Again, this is a complex number. We know how to take the modulus. This means square root of 1 plus alpha minus alpha cos theta whole squared plus alpha squared sine squared theta is less than 1. Okay, let's expand this term. This becomes 1 plus alpha squared cos squared theta plus 2 alpha minus 2 alpha cos theta minus alpha squared cos squared theta, and the imaginary term is this, less than 1. Okay, we know cos squared theta plus sine squared theta is 1, so this becomes 1 plus 2 alpha squared. Let's cancel the 1. Let's get rid of this 1. So this becomes 0. So we have 2 alpha squared plus 2 alpha minus 2 alpha cos theta. Did I make a mistake? Yeah, there's a 2 here. Minus 2 alpha squared cos squared theta is less than 1, 0, which means, let's see, 2 alpha squared into 1 minus cos theta plus 2 alpha into 1 minus cos theta less than 0. Again, did I make a mistake?
The cosine should be squared with the first term, 1 minus, on the last line, the 2 alpha squared times 1 minus cosine squared theta, right?
Okay, you tell me. Where? This term is
The
okay?
last line,
The last line, okay, here.
the cosine theta, that should be squared.
Ah, yeah.
Or a
wait.
common factor to a cosine, cosine theta is yes.
Okay, let's see. Squared is 1, so this goes here, this goes here. Yeah. Okay, I'm going to get ahead of myself again and say I have done something wrong.
Yeah, cosine is square.
Yeah, this is what you're saying, right? So this comes here, this goes here, right? And this goes here. All right, luckily this time I did it at home, so we can check.
Okay, I think.
Do you see a mistake?
Yeah, the mistake is on the second line. Cosine is square. Yeah, when you expand it, it's not a square. It's just 2 alpha squared cosine theta.
Yeah.
No.
No.
No,
I don't know this.
the next one, the next term is 2 cosine.
Oh yes.
That's only one.
Yes. You're right. Yes. Yeah. So that was wrong. So let's see. Yeah, perfect. Sorry. Okay, so this becomes 2 alpha times 1 minus cos theta and alpha plus 1, 2. Alright, now it makes sense. Okay, perfect. So we know this is positive. What about this one?
It's positive 0 to 1.
Can be.
Yeah, The maximum this can be is, there's a minus here. The maximum this can be is 0, so it's positive, and I have a minus sign missing somewhere, minus, 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 minus. Okay, let me compare it to my notes one level. Let's see. This is good, this is good, this is good, this is good. Aha, this is wrong. Why is this wrong? Minus, minus. Why is this a minus, minus? 1 minus, minus. Why is this a minus, 1 minus? It's a minus because. Oh, okay. Alright, I'm just going backward because I have done, where did I take a mistake? J, no, that's fine. J plus 1, okay. Ah, gosh, can't believe I did a mistake. Alright, let's see. Okay, J minus 1, J minus 1, J. Okay, I will have to check again, but this should actually be an alpha minus 1. Okay.
Alpha minus.
Should be this less than 0. Okay, and which gives us. So alpha minus 1 should be less than 0, which implies alpha should be less than 1. And we said alpha equal u delta t over delta x, which implies u delta t over delta x should be less than 1. Okay? And this is the stability condition. Have you seen this before, this term? Oh. Have you heard of something called the CFL number? No?
Yes.
This is a very important number called the CFL number. And I think even if you use commercial software, there might be some sort of set CFL number.
In ANSYS, yes.
In ANSYS there is, okay, yeah. So the full name of this is Courant
number.
Friedrichs Louis number. Okay, these are the 3 scientists that basically did this analysis almost 100 years ago. Okay, so I'm again sorry about the mess up. I will figure out what I did wrong. I will very quickly show it to you again next class. So now this stability condition is on what? Is on the diffusion equation, the advection equation. It doesn't matter what we did, how we discretize. When is this valid?
Upwind advection.
Yeah, this stability condition is specifically applicable to an upwinded scheme for advection. For diffusion, there was a different condition which we had derived. Okay, so there's these 2 different conditions for 2 different physical processes. When you do your simulation, you will have both of these combined. You have diffusion, advection, and pressure happening at the same time. So usually you have to check both of these numbers, this one shown here and the other one we derived, and make sure your delta t satisfies both these conditions. Okay. Again, it can get very restrictive if your delta t is very small. How do you circumvent that issue? If you're suffering from very small delta t values?
Make delta x small.
You can make delta x larger, right? That will help you with delta t, but that sort of says, okay, I will make my grid coarser and I will get a worse result in space in order to be stable, right? So it's a possible fix, but then it affects your accuracy, right? If you want to completely forget about this sort of issues with delta t, what do you do? Yeah, you use implicit schemes. So you can use an implicit time integrator for advection and for diffusion. Most of the codes that I have run are usually coded with explicit schemes. Because they're simpler to code, they're much faster in terms of computation. They're much cheaper. So yeah, we take a hit in terms of delta t, but we save a lot of computation. We don't have to solve all these matrices, the huge implicit matrices. Okay, so that's a big advantage. Okay, now, one more thing is, you can sort of logically think about what this condition means. Again, U is carrying information, right? U is carrying information about what happens to my phi. What does the top represent? U times delta t.
Delta x.
It represents delta x. Delta x is, here I've said delta x is my grid size, right?
Yes.
So what does U times delta t represent? So delta x, let's write down. So delta x is grid size, right? And U delta t is?
The distance moved in time delta.
Yeah, this is the distance that
Information.
exactly traveled by the information. Okay, so what the CFL condition is telling you is, what is it telling you?
So the information should go slower. The distance between these two,
Okay, yeah, it should go slower.
Distance should be smaller than the grid size.
Yeah, the distance traveled by the information propagation should be smaller than my cell size. So if you look at what's happening at this grid point, the information should not come from beyond over here. Okay? That would be an unstable scenario. It should come from somewhere within here, and that's a stable scenario. Okay? So CFL less than 1 implies information distance traveled by information should come from within at least, come from within at most one cell away, one cell length away. That's what this means in practical, in a practical sense. And we keep talking about this information traveling one way or another. That's because this is a hyperbolic equation. The advection equation is hyperbolic. So the equation travels with this speed, u. In our case, it's the speed of the fluid. In acoustic waves, this would be the speed of sound. Right? That's how fast the information propagates in any medium, in steel, in fluid, in air, whatever. Okay, so let me quickly recap. Today we switched from talking about the diffusion equation to we started looking at the advection equation. And I showed you a few examples of very simple tests and what can go wrong. And then we discretized the advection equation using a very simple, innocuous looking scheme, which was this one. It was first order in time and second order in space. And we realized that this is actually unstable. And then we switched to this upwinding concept where you bias your derivative towards where the direct information is coming from. And that turns out to be stable. Again, I will go through my derivation and figure out where I missed the minus sign. And I will show you next class. So homework is due tonight. Do you have any questions? Come to me. I will be in my office, or email me. I might be running around. The first project is up. Please take a look at it. Next class, ask me questions. It's, again, everything we have seen up until previous class is what you will use. Okay, it's a very simple, easy question project. Okay, any questions? Yes?
The U is always changing, right, with space?
Yeah.
And delta x is fixed, so does that mean we have to change delta t with each U?
Yeah. So that's a very nice question. I'm glad you brought it up. I totally forgot to tell you about it. So the question was, in this one-dimensional case, I have different U's at different grid points, right? And this condition that I have derived, which I have lost, here, depends on U. And this U will be different for each of these grid points. So which delta t should I pick? What should I satisfy? Should there be a different delta t for each grid node? You tell me, is that feasible to do in the simulation? You have different delta t's for each grid node. What would that do? Physically, it will mean that you only go 0.1 seconds at this node, but you go 0.4 seconds at this node. Now there is an imbalance, right? You're not at the same time, so you cannot proceed any further. So what you do is
Picking a smaller.
yeah, tell me.
Picking the smaller one, right?
Picking the
The
smallest.
smallest delta t.
Yeah, so you compute, you figure out which is the smallest delta t for all these grid nodes, and you use that for all of them. That's an okay solution. And again, if you remember, if one of my grid nodes has a very high U, then everybody else suffers because of that. So that's, again, a bad thing about explicit schemes. Going to an implicit scheme would be an alternative in that case. More questions? Okay, so let's stop there, and I'll see you next Thursday.
Because I saw you at the bus. You was going to the bus.
Yes.
I was driving that way. You was waiting for the bus because I was not sure whether you or somebody else also crossed you, so I cannot return. So you stay at this area?
Nothing else I saw yet.
I know you lived in Aventura, so from Aventura to that spot you one bus, from there to here another bus. But I'm not sure. So
I think there's another bus, right?
I actually fixed it.
Oh, perfect.
So you have to stay past
Yeah.
5 minutes before you go to like
I actually review it, but now.
So every time you use bus, right?
Just having it
Two bus. Yes,
Oh,
I know.
you know, right?
When I was there, I was using
And if
supposed to
it's
use bus,
an
but
original,
there is
and it's actually
I
received,
had
it's-
so many times for the bus. When bus system, it doesn't take.
It's just a matter of getting here.
Waiting time is.
I moved.
So
So,
you're from India?
assuming that
Bangladesh. So
If you do catch from the prints.
Anyone originate like or to come from here?
Okay.
Okay.
So, actually, so I went to Power, and I said local
Okay, so
presentation,
You are
and
running
it's,
BI, right? That opens a program, but CAS is
Being
printed.
on the call.
it,
My-
being on us, and then we
my-
got the tools first, you'll hear
Yeah.
that, all that is one of
And
the
I
things.
always-
no, you need to write, then you.
I always do room
I
mistakes.
just take this course for my lunch, because I almost.
That's our room.
What's going on?
Yeah,
No
yeah,
more
so the
credit
teacher,
left to
whoever
take
can
this
navigate.
course. So
Um,
also, you know, if I take that course, then I have to take it I also have to pay the credit and I also have to pay the something.
I know, it gets
Better
tough.
not to take credit.
They're getting a,
That's what
next at
So
I
you just start. You are
twelve
alright?
fifty-two. I was just like,
It's
here a couple minutes
Like I
ago.
looked up YouTube videos and put it on a sticky note. I have links to
Right.
it just in
I
case if I
got
forget.
students all over my
Sure,
computer.
yeah,
in the
okay.
office.
I know. The,
Okay, so yeah.
you also know
Instead of
which
DI,
this is also similar.